Welcome everyone to this machine learning seminar series of the University of Sheffield. This is for the first time we are also trying a hybrid event. So we have people in room at the Ada Lovelace room in the computer science department at the University of Sheffield and also online on Worldwide Neuro/ML. I'm pleased to welcome Dr. Shirin Dora from the University of Loughborough. We have been meeting each other on and off, but his trajectory has been, he did his bachelor's in electronics and instrumentation, and then his PhD in machine learning from Nanyang University in Singapore. And then in between both sides, he worked in industry, and then he joined as a postdoc at the University of Amsterdam with Dr. Cyril Penarts. And then he was at the University of Ulster as a lecturer in Northern Ireland for 2 years, and recently he has moved to Loughborough, again as a lecturer. Earlier his interests were spiky neural networks and biologically plausible learning, then also multisensory integration and predictive coding, and now he's also moving towards neuromorphic computing. So let's hear Dr. Shirin Dora on edge computing using spiky neural networks.
Okay,
over to you, Shirin.
Thank you. Thank you, Aditya, for the nice introduction. And thank you, Eleni, and thank you, Aditya, for arranging all of this and inviting me for the talk here. As Aditya already mentioned, I'm a lecturer in the Department of Computer Science at Loughborough University. And today I'll be talking about our work on edge computing using spiky neural networks. Okay. Okay, so this is a brief overview of my presentation. I'll first talk about predictive coding, which has origins in neuroscience. And through the description of the models that we have developed, I'll try to argue that predictive coding can support asynchronous learning and how asynchronous learning can be useful for edge computing problems. I'll follow this discussion up with spiky neural networks, focusing on two specific problems, mainly low latency classification and interpretability in SNNs. And finally, I summarize the work that I described today and also mention a brief about the different applications we have used our work for. So predictive coding is a computational theory that has been shown to account for many phenomena observed in the brain. There have been a range of computational models that account for phenomena like increasing selectivity across the visual hierarchy, attentional modulation, mismatch negativity, and many other phenomena that we know exist in the brain have been shown to be accounted using models of predictive coding. On the experimental side, there have been experimental recordings that have been shown to be supported through models of predictive coding, and these recordings have been obtained in early areas like V1 and in higher areas like IT, and also across a range of species, which include humans, rodents, and macaques. So there is plenty of evidence both on the computational side and on the experimental side that supports the idea of predictive coding as a theory that the brain might be using. So on a very superficial level, the idea behind predictive coding is that the brain builds a generative model of the external environment based on the sensory inputs it receives. And in this generative model, the brain tries to infer hierarchical representations, and these hierarchical representations provide us useful information that I'll try to describe through an example. So when we look at, let's say, a simple fruit, let's say an apple, essentially what information we are receiving in the form of sensory input is just light reflected off the surface of the fruit that is received by the retina in the form of light intensity, but our brain is actually capable of inferring the size of the fruit based on this information. So here, under a predictive coding hypothesis, the brain tries to build a generative model that can produce the same light intensity that is reflected off the surface of the fruit, and the hierarchical representations that it infers provide us information about the size of the fruit. And there are many such examples. For example, how we infer whether an object is closer to us or farther from us based on the auditory input we receive, and how we infer whether a surface is hot or close based on the sensations through skin that we receive. So there are many examples wherein we receive sensory input that doesn't exactly contain the relevant information, but the brain can extract the useful information out of it. So I hope that gives you, that convinces you that predictive coding is a strong hypothesis that has both been supported by computational side and on the experimental side. Next, I'll try to describe the model that we developed of predictive coding. And I'll start with an idea of an autoencoder, which I'm assuming that many of the people would already be familiar with. So essentially, an autoencoder is a neural network that tries to reconstruct the same input that it receives. So for this discussion, I'll assume that we have an autoencoder with a single input layer and a single hidden layer and a single output layer. Here, the hidden layer is also sometimes called as the bottleneck layer because the dimensionality of the hidden layer is usually less than the sensory input itself. And what the autoencoder does is it estimates the activity of neurons in this layer based on the propagation of information from here using the same computations that underlie neural networks. So you have an encoder that is used to infer or estimate the neural activity here. We have a decoder which has the parameters theta, and through this decoder, the prediction is generated by the network about the input that the network has been presented with. So y is a function of x and phi here. X hat, which is the output of the network, is a function of y and theta here. And our goal is to estimate the values of theta and phi such that the neural network can reconstruct the input it receives. So this is basically what an autoencoder does. And now the key idea where autoencoder differs from a predictive coding is that in an autoencoder, our latent representations here are function x and phi, but in predictive coding, we do not actually have an encoder. So you don't have an encoder, you have a latent representation y, and which is used to reconstruct the input. But then the question is like, how do you find a suitable representation y that is capable of reconstructing the input? And what predictive coding does is it treats y as a learnable parameter, just like theta. So sorry, I'm just going to remove my sweater. So, so to better understand how it works, let's consider a simple same network with a single hidden layer and a single output layer. And let's assume we are using the mean square error as a loss function. We have an x hat, which is the prediction generated by the network. We have an x, which is the actual sensory input. We can use any loss function in general, but for the sake of simplicity, let's assume that we are using a mean square error. Now, the first step is we would estimate the parameter theta over here, which is associated with the decoder. And so you do the same gradient descent stuff over here. And this is what we term as the learning step for the model. And to infer y, we use the exact same idea. We again do gradient descent on the same error e over here. And this is what we term as the inference step in predictive coding. Now, so when you actually train the network, you alternate between updating theta and y using the same gradient-based approach. And one last thing I want to highlight here is that the information that is being used over here in the learning and the inference step is available locally, which is important when it comes to edge computing, because you want to rely on information that is locally available for any form of learning to ensure that the circuits on chip are simpler. So this is actually true for all neural networks that consist of one layer, but why it is important for predictive coding is because you can do the same idea in deep neural networks as well. So let's say we want to take this to a deeper neural network. Now, so what we were doing with a single layer was we simply infer y and infer theta in order to generate a better reconstruction of the input. Now, when you want to generalize this idea to deep neural networks, what we do is we can keep on stacking layers, and each layer is simply trying to predict the activity of neurons in the next layer. So y1 over here tries to predict the sensory input itself, x, and then y2 over here tries to predict y1, and y3 over here tries to predict y2, and theta 3, theta 2, theta 1 are the associated parameters. Now, when you're simply trying to predict the activity of neurons in the next layer, your loss function is based on the activities of neurons in the next layer. So you have for this y2 hat minus y2. For this layer, you have y1 hat minus y1. For this layer, you have x minus x hat as the loss function. So you are still using all the information that is locally available for both the learning and the inference step. One important thing to note over here is that in general, when we talk about neural networks, arrows represent propagation of information, feed-forward propagation of information. But note that over here, this layer generates a prediction about y2, y2 generates a prediction about y1. So information actually never propagate more than one layer beyond. So y3 simply predicts this, y2 simply predicts this, y1 simply predicts this. So information is just transmitted to the next layer, not beyond that. Now, you might actually argue that if you're simply stacking layers on top of one another, what's the guarantee that you actually end up utilizing the capacity that a deep neural network provides? Which is a very valid question. So what we did was we introduced a small change in the loss function. So let's consider a network with two hidden layers and one output layer to better understand the change in the loss function. So when we look at the loss function for y1, we have e1, which is simply f of y1 comma theta 1 minus x, which is the actual input. So you have this mean square error function for y1. And then you have a similar loss function e2, which is for y2, f of y2 comma theta 2 minus y1 whole square. Now, if you notice carefully, you can note that there is a y1 here, there is a y1 here. But up until now, we are only using this as the loss function for the inference of y1. So what we do here is we actually try to use both these equations as a loss function while doing the inference over y1. So if we look at the first part, this is a loss function that's simply based on the reconstruction. So the reconstruction of x that is generated by y1. So when you use this loss function to infer a value for y1, you are essentially moving y1 in a direction that allows you to generate a better reconstruction of y1. But when you use this loss function to infer y1, what you're doing is you are actually moving y1 in a direction that is closer to the prediction of y1 that is generated by y2. So it's like you are actually moving the target for y2 closer to the actual prediction generated by y2. And what this does is this simple idea actually allows you to exploit how information is actually transmitted in a deep neural network. So we're no longer constrained to learning happening in a single layer and just stacking layers, but we actually exploit the capacity that exists in a deep network. And you use this idea across the whole network. So you use this idea across all layers of the network. All layers have a bottom-up loss and all layers have a top-down loss. So the term bottom-up and top-down have origins in neuroscience. So I wouldn't go into that for now. And you may notice that inference step is still local because you are essentially, so if you look at this particular layer, you have a bottom-up loss that is based on the information here, and you have a top-down loss that is based on the information here. Okay. So for inference, you still rely on information that is present in the next layer and information that is present in the previous layer, which means you still rely on information that is locally available. You don't have to do a feed-forward sequential pass and a backward sequential pass in order to do the learning and inference. So up till this point, what I have shown is that each layer has its own loss, own separate loss, which is actually used for inference and learning. And what that means is that you can actually have learning of theta3, theta2, theta1 in parallel, and the same goes for y3, y2, and y1. You can have inference in parallel. So this is where the idea differs from normal traditional neural networks, where you have a sequential feed-forward pass and a sequential backward pass. Whereas predictive coding actually allows you to train deep networks that doesn't rely on the sequential passing of information. And from an edge computing perspective, this has the advantage that you can have learning in the network happen asynchronously. You can support workloads wherein, for example, you have a deep network, but only some of the layers have errors that are higher. So you only apply learning and inference in those layers, and you don't perform any learning or inference in the other layers, thereby again improving the energy efficiency of models that you use for edge computing. Another advantage of inference is that you have low latency, because you don't again rely on forward and sequential passing of information. You have parallel learning and inference throughout the network, thereby lowering the response time for the models you use. And finally, this results in simpler on-chip realization, because you are still relying on information that is locally available. You don't need a backward pass that relies on a complicated circuitry. You could overcome this issue of complicated circuitry for back propagation by training your networks offline using GPUs, CPUs, and high-performance computing, and then porting those models to chips. But then this approach works to a good extent, but it fails when you are working on tasks that require lifelong learning. For such tasks, you need to have learning on chip possible. And this is where predictive coding can simplify the existing circuitries. So this is a recent publication in which I developed a model for predictive coding, and we looked at the generative capacities of the model. So what we used was a model that had 4 hidden layers, and it was trained using images of aeroplanes and cars from the CFAR10 dataset. And what this shows is the first row actually shows the original image that was used for training, and the subsequent rows show the reconstructions obtained from the network based on the activities inferred in individual layers of the model. So the first row over here shows the reconstruction that is obtained based on y1's prediction of x. The second row shows the prediction that you obtain when you generate a prediction based on y2 of y1, and then this prediction is actually used to generate the actual input. And the same idea is used for y3, and the same idea is used for y4. So you can see over here, because of when you use predictions that are generated from y1, these are actually represented in the first row, and these are actually better than the predictions that are generated by y4, which are present in this row. So the idea of lower and layers and higher layers is kind of opposite to normal neural networks. This layer is actually lower over here, and this layer is actually higher over here, because this is closer to the input and this is farther from the input. And that's the reason why you see this deterioration of quality of the images as you move from lower to higher layers in the network. So we also looked at reconstructing images of objects that were actually not shown to the network during training. So these are images of animals and ships, again from the same CIFAR-10 dataset. And the model can still reconstruct or can infer activities that are capable of reconstructing images of objects not present in the dataset. So what this means is that the model can actually capture statistical regularities in the images that are very generic and apply to a wide range of objects rather than the objects used in training. So based on the results I show here, we actually call this pathway of the model a generative pathway, because you can use you can propagate information in this direction to actually generate the input presented to the network. And I'll come back to this, why we call this generative, in a bit, in the next slide. So the other thing we actually did was we looked at the discriminative capacities of the network. So whether the model is actually fit for object classification. Now, note that this is a model that is trained using unsupervised learning. So we actually never present any class information to the model. What we essentially did was we actually just use unsupervised learning, predictive coding, and inferred the activities of Y1, Y2, Y3, and Y4. And then once we have these activities, sorry, this figure is actually opposite of this, like this layer is this one, and Y1 is this one, and Y2 and Y3 and Y4. Sorry, I hope this doesn't cause any confusion. So once we have inferred activities or the neural activities for a given images, we train an SVM classifier over here, and we look at the classification accuracy of the model. So what we observe is that as you move from area 4 to area 1, the classification accuracies improve for the model, which means that the model is actually making inferences that are better suitable for classification as you go from lower to higher areas in the model. And because of this, we actually call this the discriminative pathway in the model. So both the results that I showed on the previous slide and on this slide are actually obtained using the same model, which means you can actually use predictive coding to construct models that are simultaneously capable of generative tasks as well as discriminative tasks, and which is again useful for edge computing, because then you can lower the memory footprint of your models that you use for edge devices. So that's all I'm going to talk about predictive coding today. How much time do I have?
Around 10 minutes.
Okay. So next, I'm going to talk about spiking neural networks.
15.
Okay.
Because we started late, so.
Okay. So up till this point, we were talking about asynchronous learning, where the focus was actually developing models that are good for edge computing perspective in terms of learning. Spiking neural networks are known to be very energy efficient when it comes to simulation on edge devices, because of their event-based computational paradigm. So in this part, I'll focus on specific problems using spiking neural networks, but will more rely on the simulation aspect of spiking neural networks being energy efficient rather than developing energy efficient approaches for learning. So the focus is mainly on two problems: low latency classification and interpretability in spiking neural networks. So this was actually work done by one of my students, Pranav, in collaboration with the Indian Institute of Science. And what we did was we essentially introduced some simple changes in the architecture and the algorithm for training spiking neural networks. So architecturally, the first thing we did was we introduced inhibitory connections in the hidden layer. And the idea behind introducing these connections was that once you have these inhibitory connections, they introduce a competition in the hidden layers of your network, which means that once the first neuron spikes, it tries to suppress spikes generated by other neurons in the layer. And the second change we actually introduced was we determined the predictions based on the first spike generated in the output layer. So there has been a lot of work on spiking neural networks being used for classification problems, but the focus has been estimating predictions based on the output neuron that has the maximum firing rate. So again, this enables, so the moment the first spike is generated in the output layer, you can already make a prediction about the associated class for a given input. So to exploit this approach to learning, we also made some changes in the algorithm side. Essentially, what we did was we focused on maximizing the separation in the first spikes generated by the output neurons. So let's assume that this is the output layer of the network. This neuron has the first spike generated at this time, and this neuron has the first spike generated at this time. So when I say maximize separation, I'm talking about this separation between the spike times of these two neurons. So rather than training the network to have a maximum firing rate or having a desired spike time, what we do is we actually focus on maximizing this separation between this first spikes generated by the output neurons. And for this purpose, what we do is we also estimated the predicted probabilities for a given class based on this particular separation over here. So over here, Tk star actually denotes the first spike that is generated by any output neuron, and Tk is then the time of the first spike generated by the kth output neuron, small k output neuron. And this gives us the temporal separation between any two neurons in the output layer. And then based on this, you can estimate the predicted probabilities using the same softmax formulation. And what this already tells us is that the predicted probability that a given sample belongs to a given class is based on the separation between any two neurons, between the first spikes generated by the output neurons. And once we have estimated these predicted probabilities, we use a simple cross entropy loss formulation to train the network. So we tested the model on MNIST classification. We obtained 97.6% accuracy, which is not the best, which is not close to the state of the art. But the key thing that I want to highlight is this particular figure, which, so in this figure, the blue corresponds to the time of first spike for the neuron that is associated with the correct class in the output layer, and orange corresponds to the neurons which are associated with a different class in the output layer. So algorithmically, we do not impose any desired spike time on the output layer neurons, but what we do is we try to maximize the separations. So you can see from here that most of the correct class neurons fire as soon as possible within the simulation interval, whereas orange represents other class neurons which fire close to the end of the simulation duration. And this is achieved without actually imposing any desired firing time. So what this means is that depending on the data set, the network can automatically choose, okay, I have enough information now, so I should probably spike already and not wait for more information. So the idea of maximizing separation allows us to do classification by increasing the separation between the first spikes generated by neurons from the correct class and the other classes. In addition, it allows us to do low latency because it automatically pushes the correct class spikes to as soon as possible in the simulation duration. So what I showed here was a spiking neural network that actually uses a cross entropy loss in the output layer. And what this does is this improves latency, and this also minimizes the number of spikes in the network. But what we used for minimizing the spikes was basically inhibitory connections in the hidden layers. Now, what we are currently trying to do is we are trying to exploit the idea of asynchronous learning from predictive coding in order to apply this idea to all layers in the network. So the aim is to actually use a first spike based coding in the all layers. So you can minimize the energy consumptions of all layers in the network rather than just the whole network being trained on a cross entropy like formulation. The other thing I want to talk about is interpretability in spiking neural networks, and this work is done by Wahid, one of my students at Ulster University. And the key idea in this network was that we have neurons. So this is a single layered spiking neural network, and we have neurons over here which have these degree of class association. So for a k-class problem, small k-class problem, each neuron has a class association. So for example, if I look at this neuron, we have class associations that look like this, and this bar indicates that this neuron is strongly associated with this particular class K over here. And so this was the architectural change that we introduced. And on an algorithmic side, what we do is we actually learn these class associations during training along with the weights that we are learning. So we start with something like this, where all classes, where a neuron has class associations that are equal with all classes, but then we adapt these during training to get something like this, where it becomes stronger with one class and weakly associated with other classes. So the other thing we actually observed in this network is that at the end of training, there are actually many neurons which were weakly associated with all classes, which means that if you drop them from the network post-training, you do not affect the performance of the network a lot. So the other change we actually introduced was layer-wise training, which means that we add layers one by one to the network, which allows us to exploit these class associations that we have learned in a given layer while learning the weights in the next layer of the network. So we evaluated this network on the MNIST problem. We get around 98.91 accuracy, which is close to the state of the art. So for training, we actually started with a network that looks like this. So 28 by 28 inputs, 150 hidden neurons, and 100 output neurons. So just to be more specific here, that this is a network wherein the output layer doesn't just contain as many neurons as the number of classes, but it can contain any number of neurons. And since we are learning the class associations, we know which neuron is associated with which class. So we use these class associations to estimate the predicted classes. Now, post-training, what we do is we actually drop neurons like this, whose class associations do not change significantly from their starting point. And what we get post-training is a network that looks something like this. So we have dropped more than half the neurons in both the output layer and the hidden layer. And we also tested this approach on the question MNIST dataset, where we obtain around 94% accuracy, and starting with the same network, but with only one hidden layer, we again were able to drop the number of neurons to 55. So in this case, we are actually training the network layer by layer. But again, our idea is to bring in predictive coding in order to exploit this layer-wise learning while retaining the capability for interpretability. And the other direction that we are exploring with this network is of lifelong learning. So lifelong learning is basically the task. So it's a problem wherein you train a single network on multiple tasks. So you train a network on task A, and then you train a network on task B. And because neural networks suffer from the problem of catastrophic forgetting, when you train the network on a different task, it forgets all about the previous tasks. So the problem of lifelong learning is all about preventing catastrophic forgetting in neural networks. Now, there have been approaches which look at memory-based approaches and which look at selective synaptic updates for lifelong learning. But what we are actually exploring is the idea of these class association strengths, because as I said here, we actually drop these neurons whose class associations have not been changed significantly during training. So what we are exploring now is we're actually trying to use these neurons instead of the neurons like this, which have higher class associations for a given class, in subsequent tasks. So for task A, suppose we ended up with such a network after training on task A, during task B, we actually rely on neurons like this, which have very minimal changes in their class associations. And this enables, again, the network to actually prevent catastrophic forgetting. So, to summarize, the overall goal of my research is to build an interpretable, efficient, lifelong asynchronous learning framework using deep spiking neural networks. And our current focus is on supervised predictive coding in spiking neural networks. So what I presented today is unsupervised predictive coding, but we are doing work now on supervised predictive coding so we can actually train these networks for machine learning tasks. And what I presented today was work with rate-based neurons. And what we are working on now is spiking neural networks, predictive coding for spiking neural networks. And we have already done a lot of work in this direction. This is in collaboration with my past colleagues at the University of Amsterdam. I haven't presented this work, but if you are interested, we can talk more about that as well. And the other problem that I'm interested in is lifelong learning and low latency. Again, the ideas that are imported from an edge computing perspective. On the application side, I focus on drones and swarm robotics, which are basically mostly focusing on aerial swarms. Resilient multi-agent system, which is basically the idea of exploiting multiple agents in order to improve the resiliency in tasks. So if one agent goes down, there is another one to actually replace and complete the task. And finally, multi-sensor fusion, which is the task of integrating information from multiple sensors in order to perform some downstream machine learning problem. Thank you for listening.
Thanks a lot, Shirin. We open the floor for questions first from our audience here.
I have one about prediction coding, because you're always plotting your arrows in the network feedforward.
Yeah.
And I'm wondering, how do you infer the presentation from unseen data? Are you inverting the matrices? Because if unseen data, it means that you have not trained the network to find the representations, right? So what is the operation from unseen data?
So
you use to generate from unseen data representations.
So it's at a layer level, we have the same computations that you have in a normal neural network, like the matrix multiplication, input times the weights, and you can apply any activation function you like. And we do this at each layer level. So it's the only difference over here is that you're actually not propagating the predictions forward, but then you're trying, since you're actually making, so let's say we talk about Y4, it generates a prediction about Y3.
Can I ask you, say we have a new image that you never trained. If you train, I think it's clear how you can estimate the efforts that you explained to us.
Yes.
But say now there is an image that you've never trained in a network. What is the process to generate the latent? Because I assume you have the x hat equal, I was assuming, with the image, but then the network is feedforward. So, of course, if you've estimated previously weights, you probably invert mathematically, but maybe you're doing something different.
No, so let's say you have an image that was never shown to the network. You present it here. You start at a Y1 that's completely random, and then you again. But then when you, so the network is trained now, so we do not update any weights anymore. So θ1 is actually fixed. We start at a random Y1. But then we use the same mean square error or any other error, just do gradient descent on that to get better inferences about Y1.
Okay. So you're actually training that representation.
Yes.
Okay.
So
thank you for the clarification. Thanks.
I have a question on the asynchronous learning. You say that the Y, let's say Y2 will move in a direction to get closer to Y1 and at the same time to get closer to Y3. But you say that this happens in parallel, so this is an in parallel inference. But somehow you have to make sure that the latencies between the layers are like in time, so that the information is available that at the same time step from Y1 from Y2 to get that equivalent information at the same time step from Y1 and from Y3, or only, like, because they are dependent, so I'm a bit like confused. How do you decouple the relationship between the layers and make them asynchronous learning or happen independently? However, they have to be dependent somehow, or they are dependent, like because of the top-down, bottom-up.
So the way we do is like we have a global time, which we use to update all layers in the network in parallel. So basically, just to be more specific, let's say we just talk about y2 over here. At time t, it will actually use the representation, the prediction generated by y3 at time t based on y3 now, but it will actually use y1 from t minus 1. So its prediction will be based on y1 at the previous time step, but the prediction it receives from y3 is at the same time step.
Oh, okay, I see. So it wouldn't use y2 would not use the y1 at time t. It would use from the previous time step.
Yes, yes.
It's not like a clock that everyone will follow or the layers will follow. Like there will be. I was thinking that y1 will be updated at time t, and this data will be available for y2 to use at the same time step.
So you can do that, but how we do is like we do everything in parallel, which means that like every subsequent layer, so like y2 will predict y1 at t minus 1, y3 will predict y2 at t, and y4 will predict y3 at t plus 1. So like there is a one time step gap.
I have another question on that. Did you observe any level of sparseness on the different, on each layer or each layer, where like that high order, you call the y1 the lower order and y4 the high order. Did you find that, let's say, y1 were more sparse than y4?
So we actually saw the other way around. Y4 was more sparse than y1, but then the behavior for sparseness was a lot more complex compared to selectivity. So in this paper, we actually look at sparseness as well, but then for selectivity, it's a straightforward thing. Like it increases from lower to higher layers in the model. But for sparseness, what actually happens is, let's say I introduce sparseness in this layer, apply, let's say artificially, some form of regularization. Now, because of the loss function, because of the loss function is designed, it will actually introduce sparseness in all layers in the network. So sparseness kind of spreads throughout the network because each layer is trying to predict the next layer. So sparseness spreads, but the thing is that as you move away from this layer, this effect becomes weaker. So you don't see a systematic increase or a systematic decrease in sparseness. Sparseness can exhibit more varied behavior.
Oh, it's not like it's not get diluted across from y4 to y1.
No.
There's no systematic pattern.
No, there's no systematic pattern.
Okay. Thank
Yeah.
you.
I have a question that maybe, I haven't understood too well, but if you get a new example and then you want to say do classification on the example, but you've already learned all the like mappings between the layers, so that's like your representation or whatever, and then you go and map each layer backwards using what you described, just then another training procedure on each test example. So I was just wondering, like you were saying it was useful for like low latency applications or like edge computing applications. How does that compare, like, because in a normal neural network, obviously when you have a test example, you just map it forward, no training required. Whereas here, there's another training procedure. So how does like the latency of those two things match up?
So that's a good question. And so what we actually did a recent study wherein we actually looked at VAEs for generative modeling, and we looked at predictive coding for generative modeling. And so that study was actually more on multi-sensor fusion. And we do observe some latency because you have this inference step. So VAEs were actually faster in comparison to predictive coding, but as you make the network deeper and deeper, this effect becomes weaker. So VAEs have more latency, but then because of this parallel inference, the depth actually sort of reduces this effect.
Right, that makes sense. Thanks. I also had another maybe smaller question. Are you allowed to just use whatever architecture you want for the layers between, like, so you can use a convolutional architecture? Okay, right.
So you can actually use, so in this paper, we actually didn't use a fully connected network. We use a more like locally connected convolution kind of thing. So you can use any architecture.
Great, thanks. Oh, sorry, Felix.
Yeah, I was just thinking, how have you studied the overfitting in these models? I mean, like, you have so many parameters here. How do you regularize your network? Or?
So we do use regularization, and unlike normal networks, we use regularization for both weights and inference. So our Y are also regularized because they are also learned like normal weights. So we didn't see overfitting in terms of a generative modeling. We did this for both this paper and also for multi-sensor fusion. We didn't see any overfitting. But I think overfitting will be more a problem when you talk about supervised problems, wherein it's easy to actually see because you can compare the training and testing performance. But we are still working on the supervised side of things, so I have less clarity on this actually.
I have kind of the same question because from my perspective, I see a clear maybe problem of identifiability because you're optimizing like on the theta and on the y. And how are you assured that for next image or something else, you are already capturing something with the theta? Because when you're changing your inputs, you're changing all the y 1, 2, 3, 4, and maybe you have optimized just on the y and not quite on the theta. So when you're moving from one image to another, maybe you have captured like almost nothing, and you cannot decide whether you optimize well on one side or the other. So how do you interpret this kind of thing?
So let me just get the question right. So you're saying that since we are updating both theta and y for each image, will it not be a problem whether the actual characteristics are captured by theta or y when we go to the next image?
Yeah, we don't really know.
Yeah, so what we actually do is we actually use a much lower learning rate for y, and we use a much higher learning rate for theta. And this actually ensures that this kind of problem doesn't happen in the network. Yeah. Okay, thank you. Yes.
Yeah, question.
So when you're talking about multi-sensor fusion, you say that probably you're using drones, say for instance you're using drones along with say satellite data.
Yeah.
So how do you work on the ground sampling for very small objects, like in terms of object detection?
Yeah.
So how do you work? Like how do you work on the ground sampling? Because obviously it's different. So it's taken differently when it comes to maybe the VAE or the depth.
Yeah.
So how to work?
So sorry, just to understand, the question is about like the difference in
Yeah,
the
just talking
sampling.
about the different how is the ground sample distance now? Because obviously it's going to be different because it's multi-sensor data.
Yeah.
So how is it mapped when it comes to the VAE or the generative?
So is
I'm talking mainly about the application.
Yeah.
The end that we are taking.
yeah. So it's about like sampling differences in the sensors you are using.
Yeah, sensing when you are fusion and when it comes to probably input into the model.
Yeah.
Because then when it's very small object, probably taken from very large height, say instance drones.
Yeah.
Probably it is difficult. So that's it.
So so I didn't actually talk about the architecture over here that we used for multi-sensor fusion, but let's see, where's the code? Sorry. So when we actually use predictive coding for multi-sensor fusion, let's say you have this block for, let's say, handling visual input, and let's say you have this block for, let's say, handling tactile input. Okay, so what we actually do is we actually use the representations in these two to actually as an input for representations here, which is actually multisensory. So now what we do to handle the sampling issue is that we actually, let's say a sampling for V is much higher than the visual sampling is much higher than the tactile sampling. So we actually do much more updates here and much fewer here and here.
By updates, you mean interpolation?
By updates, I mean the learning, the theta, and the inferences. Yeah. Okay.
Thanks. There are one or two questions from the audience online.
Yeah.
One of them is whether, so Eddie thanks you for the great lecture, and do you think the use of ENN framework for backpropagation will improve the effect? So I guess you want to see how backprop compares to.
Yeah, so there have actually been some works in the direction of using predictive coding as a means to approximate error backpropagation. And so like some of the recent results suggest that this is possible to a good extent under certain assumptions. But I mean, there have actually been many efforts in the past on improving error backpropagation, like by parallelizing works like those by Timothy Lillicrap, where he looked at feedback alignment, and other works which actually try to parallelize. But I don't have a clear idea as in how predictive coding approach may directly improve error backpropagation, because these are two very different learning paradigms. So like, maybe needs to be looked into a bit harder to see if there is a clear improvement possible for error backpropagation.
But if you just compare without trying to borrow one from the other, if you compare performance,
Performance in what sense?
like the ultimate, say, classification accuracy.
So you can get same levels of performance with both. See, the thing is like for predictive coding, there is like, let's say 5-7 years of research, but then for error backpropagation, it's been around since 1980. So there has already been a lot of improvements. And for our work, we actually didn't use anything like dropout, anything like patch normalization. So there are a lot of techniques that people use to make deep networks work well. Given that context, predictive coding can give you like, so for, as we saw that so there have been some works on MNIST where we can achieve 90, 97, 98% accuracy. It takes you close, but it doesn't get better than error backpropagation, doesn't hit the same levels. But I think once we try more things, it's possible to get there.
Thanks. Another question, but I guess this is pretty general, which is, are you using rate-based model? Which neuron model is STDP being used? But I guess you've already answered that this is spiking neuron models, and of course there is no STDP here. Or is it related somehow to STDP, the kind of?
Yes, so we use a supervised kind of STDP wherein we use class information with STDP. So we have already learned the let's say the association strengths for the neurons. So we do STDP in a way that exploits this information. So let's say you would actually use a positive form of STDP to increase the weight for classes that are strongly associated with the current sample, and do the opposite for other classes. So we use form of STDP, but not as in neuroscience. It's not unsupervised anymore.
Okay. So thanks, Shirin. So we thank Shirin again, and
Thank you.